In this recording, we're going to see an example of a way to solve the Towers of Hanoi problem using Java. The Towers of Hanoi is a mathematical game where the goal is to move all the disks from one peg to the other. So you'll have some sort of, typically it'll be wooden, and it'll be a wooden platform with three pegs, a starting peg, a temp peg, and a goal peg. And the starting peg will have some disks of different sizes on them, arranged with the larger disk at the bottom and the smaller disks at the top. And the goal is to move all the disks from the starting peg to the goal peg using three rules. Number one, you can only move one disk at a time. Number two, all disks have to be placed on some peg at all times. The only exception is the one disk that you're moving at that time. And finally, a larger disk cannot be placed on a smaller disk. Now it turns out it doesn't matter how many disks you have, you can always solve the Towers of Hanoi problem with three pegs. There's lots of implementations of the Towers of Hanoi online that you can play with, so we'll use this example to see how we solve the problem. So it turns out the way to solve this is to move all but the bottom disk to the temporary peg, and then move the bottom disk to the goal, and then move those, in this case it would be three disks, to the goal peg as well. So to move these three here, first I'm going to move the top peg here, move this one here. Now notice I can't move this to either place, but if I move this disk here, that's a legal move, and I can move this disk here. And then I think it should be clear how we're going to stack those up. So now I've moved the top three disks to this peg. This disk is now free to move. And I repeat what I did before, just using different pegs to free up this disk. Now this disk is here. And then I think you can see at this point how we solve this. We move these over. So it turns out we can generalize our solution to the Towers of Hanoi problem into a fairly simple recursive solution. So if we want to move n disks from peg A to peg C, whatever those pegs are, we're going to move n-1 disks from peg A to peg B. That's our middle peg. We're going to move the bottom disk from peg A to peg C. That will put the bottom disk on the target peg. And then finally, we're going to move the n-1 disks that we originally moved to peg B, the middle peg. We're going to move all of those to peg C. So we're going to write a class that's going to let us solve the Towers of Hanoi. And we'll make a Towers of Hanoi object. And here we'll instantiate in our main method. And then we just call the solve method. It's always easy to solve a problem if you have a method that does it for you. So here, let's see what happens when we run. You'll see that it's going to give you directions. Move the top disk from peg A to B. Now move the top disk from peg A to peg C. Then from peg B to peg C. And if you think about this, this is essentially what we were doing when we solved the Towers of Hanoi problem. And this was a size 4. And it turns out you can have as many disks as you want. And surprisingly, no matter how many disks you have, you can still solve the problem. So let's take a look at the code. And if you notice my slider bar, there's not a lot of code here. Think about how complex that problem is, or at least it seems, I guess I should say. It seems really complex, but there's not a lot of code. My Towers of Hanoi class has one data member. That's the total number of disks. And my constructor initializes that data member. Okay, and we're almost halfway through the code now. So we have a method called solve. Solve is going to call move tower. We're going to pass it the number of disks, and that's the number of disks we're going to move at each step. And then we have from tower A to tower C using tower B as our temporary tower. So C is the goal, and so B is the empty one, I guess, in that case. And so you would use it to do your n-1. So then here's all the logic of our program. If we're moving one disk, well, we just move it from the start to the end. We don't care about the temp because we don't need it. If we have more than one disks, we move n-1 disks from the start peg to the temporary peg using whatever that goal was as our temp in that move. Now, once we've done that, n-1 disks are now on the temp peg, and that means the end peg is free, so I can move that bottom disk from the start to the end. Then I move those n-1 disks. Now remember, we moved them to the temp peg here, so I move them from the temp to the end using that starting peg as my temporary thing. Sometimes recursion can be sort of hard to understand because, well, where is it doing all this work? Well, the recursion is doing the work for you. The recursion is saying, when you call move tower with 4, it calls num tower with 3, which calls num tower with 2, which calls num tower with 1, and that's when you actually move this disk. And as it's doing those calls, it's remembering what it needs to do. Once it returns here, it moves that one disk, and then it calls this method to move the remaining ones. Hopefully this example gives you some idea of the real power of recursion. It really is amazing how simple recursion can make some problems.